In the previous video, we discussed about linear data structures. So in this video, let's focus more on the non-linear data structures. So as we discussed in the previous video, linear data structures are those where the data is actually organized in a sequential manner. So in non-linear data structures, it will be the opposite. So you won't have data organized in a linear fashion, but rather, as the name says, it will be non-linear. So just to give some examples of non-linear data structures, we basically have something called graph, and we have trees, we have sets and dictionaries. So in this video, we'll be focusing more on the very common ones, which are like used in most of the problem solving like algorithms. So we have graphs and trees. Sets and dictionaries we'll maybe look at in some other video. So let's start with graphs. So what is a graph like? So graph is usually denoted by the letter G, and it is actually a function of V and E. Now here this V is basically a set of vertices, let's say ABC, and E is a set of pairs actually. So every pair in this set will include the like two of the vertices in this set V. Now this every entry in this set E is actually called an edge. Here every entry is basically a vertex. So a graph is a function of vertices and edges basically. Now let's just consider an example. So this can be thought of as a graph. Here the set V would basically have 1, 2, 3 here vertices, and edges would be, if you consider 1 to 2 is an edge, then from 1 to 3 you have an edge. Similarly from 2 you have an edge to 1, and then to 3, and then again from 3 to 1, and 3 to 2 basically. So this is your set of edges, and this is the set of vertices. Now in graphs we basically have two types. So there is something called an undirected graph, and there is something called a directed graph or a digraph. Now whatever we saw here, this is an example for an undirected graph. What an undirected graph means is that between two vertices, whatever edge is there, so here if you see there are two vertices A and B, the edge connecting these two vertices A and B is actually same as the edge connecting the vertex B to A. So these two, if they are same, then such an edge is called an undirected edge. And a graph where every vertex is connected with an undirected edge is basically called an undirected graph. And a directed graph would be the other way around. Like if you have a vertex A and then a vertex B, the edge which is connecting these two vertices should be a directed edge, which means that A to B is basically not equal to B to A, because this is kind of like a directed edge. So an edge from A to B will never be equal to an edge from B to A. So from B to A you will basically have an edge pointing this way. Now in this case, this edge, this vertex will basically become the tail of this edge, and this would be the head of the edge. Okay, so apart from this, we also have some other types. Like there is a sparse graph, then we have something called dense graph. We also have a completed graph, a complete graph basically. Now a sparse graph is a graph wherein the number of edges are like very less when you compare it to the number of vertices. Like relatively it's very less. And the other way around is the dense graph, where the number of edges connecting the vertices in the graph are relatively very high. So just to see as an example, maybe this would be considered as a dense graph because you have a lot of vertices connecting lot of edges connecting the vertices in the graph. But the same thing, if you want to maybe have a sparse graph out of this, then maybe this would be considered as a sparse graph. We can have like some more. So this might be a dense graph, and this might be a sparse graph. And what is a complete graph? So a complete graph is basically a graph in which for every pair of vertices there is an edge connected. So this would be your complete graph. Okay, so just to recap, graph is nothing but a function, it's represented by the letter G, and it is a function of V and E, where V is a set of vertices, E is a set of edges. And like there are basically so many types. Like majorly you classify graphs into undirected and directed graphs. And then you also have graphs of here undirected means the edge whatever is connecting two vertices in a graph is undirected, which means edge from A to B is actually equal to edge from B to A. Directed means it is not equal. It will be like pointing from one edge to other edge. Sparse is a graph wherein the number of edges are basically relatively less to the when compared to the number of vertices, whereas a dense graph would be a graph wherein the number of edges are relatively higher when you compare it to the number of vertices. A complete graph is a graph wherein for every pair of vertex in a graph you have an edge connected. So that is a complete graph. So this is just the basics of graphs. I think next we can maybe go ahead and look at how you represent graphs. So graph representation. Graph representation is basically done in two ways. One is called the adjacency matrix. This is one way to represent a graph, and the other way is actually adjacency list. So we'll just discuss both of these methods to represent graphs. So if you consider adjacency matrix, then this is actually an n cross n Boolean matrix. So this is a Boolean matrix. And n here is your number of vertices. So whatever vertices you had, so the number of vertices will be n here. And since this is a Boolean matrix, you would basically have entries in the matrix as either 0 or a 1. So here 0 entry in the matrix means that, so let's assume this, okay, we'll just consider this graph, or maybe let's take another example. So let's have this graph. So if you want to represent this graph using adjacency matrix, then we will first, here the number of vertices are 3. So I'll just create a 3 cross 3 matrix. Since this is a Boolean matrix, they would be filled with zeros and ones. Now, if an entry is actually set to 0, that means there is no edge from, okay, let's just take an example. So from 1 to 1, so this would be, let's assume I columns, and these are your j rows. These are your I rows and j columns. So here this entry would basically tell you that, this will tell you if there is an edge from ith node to the jth node. So from ith node to the jth node, here both are 1. So is there an edge? Since there is no edge connecting 1 to 1, you'll basically have this filled with 0. Now, is there an edge from 1 to 2? Yes, so you'll have it 1. But from 1 to 3, there's no edge, so it will be 0. So if you consider 2, so from 2 to 1, is there an edge? Yes, so you'll have 1. 2 to 2, there is no edge, so 0. 2 to 3, there is again an edge, so 1. So similarly, for 3 to 1, there is no edge. 3 to 2, there is an edge. 3 to 3, again, there is no edge. So this is how you basically represent a graph with adjacency matrix. Now, how do we represent graphs using adjacency lists? So adjacency list is actually a linked list, which we discussed in the previous video. So we actually maintain a linked list for every node in the graph, every vertex in the graph basically. So if you just consider this, so here we have 1, you have 2, and you have 3. So we'll basically have 3 linked lists for every, since there is like 3 nodes, so we'll have 3 linked lists maintained. Now, what will, how we'll represent this graph is basically the list for every node in the graph will actually be pointing to another node, which would be the, all the vertices which are actually connected to this vertex will be pointed, will be linked in this. So in other words, you can just say that whatever columns for the particular node have ones, those will have a separate node connected. So if you have one, since one is connected to two, you'll basically have a pointer pointing to one more node, which is your two. So similarly for two, you'll have a pointer pointing to one and a three, and for three, you'll basically have a pointer pointing to two, and this will be your null. So if you just map it to your adjacency matrix, then for one, whatever column has a one, you would basically have a node. So again, like two, all the columns wherever there is a one, so you'll basically have those nodes. So this is one more way of representing graphs. Now if you consider a sparse graph, so it would be easier to like represent a sparse graph using adjacency lists, because since the number of edges are very less, it will actually make sense to use adjacency lists because they will actually consume less space. But if you talk about dense graphs and use adjacency lists to represent dense graph, then the amount of space needed to represent this would be more, because you'll have a lot of data here. But in such a case, it's better to like use the adjacency matrix. So these are the two ways in which we basically represent matrices, the graphs. Okay, so apart from this, there is one more concept called weighted graphs. So what a weighted graph is basically, so it's kind of the same graph, but for every edge there would be some weight associated. So this would be useful in solving problems like the traveling salesman problem, which we'll discuss in the upcoming videos. Now, how do you represent a weighted graph is basically it's the same method, adjacency matrix and adjacency list. Now, we saw that adjacency matrix was a Boolean matrix, but in this case, it will not be a Boolean matrix, but like wherever we were representing one, wherever we were putting one to represent an edge, we would basically have to put the weight instead of just one. So we'll first initially maybe fill it with minus ones, and then so there is no edge, so it will be minus 1. From 1 to 2 there is an edge and the weight is 5, so you'll basically put 5. Here it will be 6. So from 2 to 1 there is an edge and its weight is 5, there is no edge, and 2 to 3 is also no edge. 3 to 1 again there is an edge with the weight 6, 3 to 2 and 3 to 3 there is no, so you can maybe fill it with minus 1. This is the way in which you will represent a weighted graph. And if you consider adjacency list, then again it will basically be having all the vertices, but apart from just the vertex, you'll also have to store the weight. So it would be like 3 and 6 you'll store here. Again for 2 it would be like you'll have 1 but along with the weight, and for 3 again you'll have a linked list will be pointing to 1 and 6. 6 would be your weight. So this is the way in which we represented a weighted matrix. Okay. So apart from this, there are some properties which we'll have to know of the graphs. So some of the like properties which we have to be aware of is the path and the cyclicity in graph. So what is meant by path and what is cyclicity? So path is nothing but, so let's say we have two nodes, we have two vertices, 1 and 2. Now we say that there exists a path between 1 and 2 if there is a sequence of vertices connecting 1 and 2 sequentially, like there is a sequence of vertices basically which connect 1 and 2. So there is a sequence, if you see, it starts at 1 and ends at 2, and there is a sequence of adjacent vertices connecting these two. So here we say that there is a path from 1 and 2, from 1 to 2 basically. And similarly, cyclicity is like we say that there exists a cycle in the graph if there is a path starting from one vertex and ending at the same vertex. So it should be like it should start at one vertex and end at the same vertex. Then we say there is a cycle. One more condition is that we shouldn't repeat the same edge. So it shouldn't be like you go from this and then you come back to the same node. This is not a cycle. So this would be your cycle basically. It starts at the path starts at one vertex and ends at the same vertex, but there is no repeated like traversing of the same edge. Okay, so we also talked about complete graph. There is one more graph called connected graph, one more type. So a connected graph is basically a graph wherein there, like for between every pair of vertices, between every pair of vertices in the graph, there should be a path. So if there is a path between every pair of vertices, then it is called a connected graph. So if you see from 1 to 3 there is a path, from 1 to 2 there is a path. So if you consider every possible pair, there is a path existing. So such a graph is called a connected graph. Now if there are no cycles, then you basically call that as an acyclic graph. So all the different types of graphs, just to recap, there is undirected, there is a digraph, then we have sparse graph, we have a dense graph, we have something called the complete graph, and we also have connected graph, we have a weighted graph, and there is an acyclic graph as well. So these are multiple types of graphs which we just discussed. Now, one of the types of graph, so what is a tree? So tree is actually a type of graph. Now it is a graph which is acyclic and it is connected. So acyclic means there are no cycles. Connected means every like between every two pair of vertices there is a path basically. So if you just consider this graph, whatever we saw, so this is also a tree because this is not cyclic and between every two pair of vertices there is a path existing, which means it's connected. So this is a tree. In more general terms, this is called a free tree. Now, if you see, like since there is a path between every, I mean, since this is a connected graph, there is one more type of tree which is called a rooted tree. So what this means is, since every pair of vertices has an edge, I mean, has a path, we can actually make use of that property and arbitrarily like select one vertex out of these, pull it up. So let's say we pick this vertex, you pull it up, and then whatever vertices are there connecting this particular pulled up vertex, you just move it to the next level, something like this. So this is a free tree, and if you have an arbitrary vertex pulled up, then it will become what is known as the rooted tree, and this would be your root node. I mean, the rooted tree is like so common that we never call it rooted tree, we simply call it a tree. So tree is usually considered a rooted tree, and such trees we rarely like make use of. We'll always implement trees in the form of a rooted tree. Okay, so there are some terms which we should be aware while dealing with trees. Now let's assume this is a tree. We have a tree, let's assume. So if this is a tree, then there is something called level, there is something called height, and then the depth. All these terms we should be aware of. Now level of let's say level of a node we'll consider. So this node, if you want to see what is the level, then this level would actually be the number of edges from the root node till that node. So the level of the root node would always be 0 because there is no edge. Level of this node would be 1, then it would be 2, this would be level 3. So level is actually the number of edges connecting from the root node till that node, that is the level. And level of the tree would basically be the highest level, maximum level basically, that would be your level of the tree. So now that the level is done, height is, okay, we'll talk about depth first. So depth of the node is basically, so let's say this is our node. Depth is actually the length of the path connecting the root node to that particular node. So that would be your depth. and height is basically the longest path from the root to the leaf. I mean, whatever leaf nodes we have. Okay, so this is the root node. Leaf node is actually the node which has no children. We'll talk about roots, I mean leaf nodes and other things later. So height is basically the deepest path basically. So that will be your height. Depth of a node is the number of edges connecting this node till that particular node. That would be your depth. Apart from these three terms, there are some more terms like there is something called ancestors and descendants. So if you consider some node, let's say n, ancestors of this node would actually be all the nodes which are in the path from the root till that node. So if you consider, let's say 4, this node, all ancestors of this node would be actually the nodes which are connected, which are there in the path from the root till that node. So 1 and 3 are its ancestors. Descendants are actually all the nodes in the path below 4 basically. So it will be like 8. 8 is the descendant of 4. So those are the ancestors and descendants. Now 4 will also be an ancestor of itself. So if you exclude 4, then all the other ancestors will be called as the proper ancestors. Okay, apart from this, if you just consider, let's say there is like only one single edge if you consider. So in such a case, this node would be your parent, and the descendants, the immediate descendants would be the child nodes. And whatever descendants are there for this node at the same level, they will be called sibling nodes. So this is the parent, these are the children, and these two are siblings of each other. Apart from that, there is something called leaf node. Leaf node is a node which has no children. So if you see, this is a leaf node, then this is a leaf node, this is leaf node, this is also a leaf node. All these nodes, they have no children, so those are termed as leaf nodes. Okay, so these are some of the terms which we should be aware of. Now there are some types of trees. We have something called binary trees, we have something called balanced trees, and we have binary search trees. So binary tree is a tree wherein for every node you actually can have at most 2 children. So this will be your binary tree. So you can have at most 2 children. You cannot have more than 2. So this wasn't a binary tree. Now what is a balanced tree? Balanced tree is like so whatever the number of nodes towards the left and the number of nodes towards the right of a node should be equal. So these two numbers should be equal. Then only it will be termed as a balanced tree. So this is a balanced tree basically. And binary search tree is a tree wherein the node value of the parent and is in such a way that all the nodes towards the left have values less than the parent. So it can be maybe something like this. And all the nodes towards the right of the parent should have values maybe greater than. Okay, so this is not a binary search tree. I'll tell you why. So let's consider 8. So all the nodes towards the left of the parent should actually have values less than the parent. So if you consider this would be a binary search tree. Now again, this should be a parent, so all the nodes towards the left should have values less, and towards the right should have values more. So if you consider 8, again towards the left everything is less, and towards the right everything is more. So here again this should be a parent, everything towards its left should be less, and everything towards the right should be more. This is a binary search tree. This one is not, because like towards the left here 10 is like more, so this won't be a binary search tree. This one is a binary search tree. So these are some of the types of trees. So this is it regarding the most commonly used non-linear data structures like graphs and trees. So that's it for this video. Thank you.